Okay. Very good. So the format will be 25 minutes you will speak and 5 minutes for questions. I'll let you know when it's around 22, 23 minutes. Okay. Hello. Can you hear me,
Sorry.
Manuela?
Yes, I'm sorry. I had forgotten to unmute myself.
Okay. So I was just saying it's 25 plus 5 for questions. So around minute 22, I'll let you know. Okay.
Okay, thank you.
Okay, so our first speaker for today is Manuela Kulaxizi, and she's going to tell us about conformal correlators and black holes. Please go ahead.
Hello, thank you all. Thank you very much for the invitation. I hope you can hear me well. I'm really sorry I couldn't be physically present there. It was a long desire to come to Corfu and to participate in the meeting, but unfortunately it didn't come through. Hopefully next year's. So I'm going to talk about a series of works that I've been doing in the past few years, and they have to do with trying to understand black holes in holography by studying conformal field theory correlators. So we all know that the holographic principle states that certain quantum field theories or conformal field theories have a completely equivalent description in terms of gravity in anti-de Sitter space. And the objective of this work, or the long-term goal rather, is to deconstruct in some sense the holographic principle in order to learn more about gravity. So this is something that it's an opposite direction than the one that's been used mostly holography about, which was to study to understand strongly coupled quantum field theories from studying weakly coupled gravity. So questions that you would like to address are what type of theories may have holographic descriptions or putting restrictions on the type of theories that you can have, that you can describe this way, and exactly what kind of physical consistency conditions you need to impose and how do those restrict your space, and obviously learn something perhaps about black holes, although this is like a long-term goal. I'm not sure we'll learn too much about that today. So here we're going to discuss and consider a class of theories that we will call holographic CFTs, but by that I will not refer to any specific CFTs that I know have some gravitational dual description, but rather I will refer to a general class of theories which have specific characteristics, at least a minimum set of characteristics. And these are a set of working assumptions that we have. That's that the CFT has a stress tensor and also two large parameters. One would be the number of degrees of freedom. Usually for an SUN gauge theory, it's the number n. Or generically, it's the C, what we call the central charge of the CFT, or the coefficient that determines the two-point function of the stress energy tensor in higher dimensional theories. And we will consider taking this parameter to be very, very large and expanding around that. So for a correlation function, which is the one that we're going to deal with, which is made out of two identical, let's say, scalar operators. The first term at infinite C is the disconnected term, where we have the product of two-point functions, and then we have corrections at 1 over C and further. And the other important scale is a large gap. This gap is in the spectrum of the CFT. So what we want to say is that generally we have like maybe infinite operators or many operators in a CFT, but we're going to split, let's say, the spectrum of the CFT in two by putting a gap between a certain class of operators, which will be a finite number of primary, what we call single trace operators, which will have only spin up to 2. This will be like a set of the building blocks of our theory. And then other operators will have a parametrically much, much larger conformal dimension than those. That's why the gap is given by the conformal dimension of these operators. This is analogous to taking like a large coupling. as happens in n = 4 super Young-Mills, which is the prototype example of holographic CFDs. So what do we mean by single trace primary? This is a nomenclature that we, again, take a loan from the standard examples of SU gauge theories, but now we won't think of that necessarily, and we just assume that we have some building blocks. This can be only up to spin 2, so the maximum that we can have is a stress energy tensor, the rest will be scalars or vectors in our theory. And then we'll have double, and what we mean by double and triple and multi-trace primaries, we mean by, excuse me, we mean composite operators made out of these building blocks, maybe only one or two of them, by inserting derivatives and boxes in between. Of course, this is schematic representation. In principle, you have to make the appropriate primary from this kind of construction, so you have to subtract some terms, but roughly speaking, a normal order thing, composite of this type will be what will be after when we're discussing double and multi-trace operators. And there are some rules about the behavior of our theory at large n or large central charge that we will follow. So our assumptions that we know that are valid in most cases that we have dealt with, which is that the 2-point functions behave like have a term of order 1 for all these building blocks of the theory. This is what we call single trace primaries. And then for everything composite that we build out of them, we can have the 3-point functions will be order 1/c without them. And for composites, as you see here, that are made out of 2 different operators than the one that we have here, we expect that it will behave like 1/c. If we have 2 operators that are the same, it will be order 1. And there will be like an operator here, the stress energy tensor that we'll be dealing with, whose leading behavior will start with 1/√c, 1/n, for the standard 4-dimensional case. Now, there's been a lot of progress in studying what we call holographic CFDs, so CFDs with these characteristics, these universal features. And there were several important results. The work really in the field started with the seminal work of Hemskerp and Adonis, Polchinski, and Sally, who studied the crossing equation for a conformal field theory under these conditions, these holographic CFDs, and understood that this implied a structure of a local gravity theory. So the number of local bulk couplings that we can have matched, of 3-point couplings matched the solutions to the crossing equation for a 4-point function. And then there was even more work. There was that showed that unitarity, or rather causality, one actually is derived from the other, implied that Einstein's theory of general relativity is the only consistent description in the limit that we are discussing, so at infinite delta gap. Okay, so for example, we could have couplings of the type of Gauss-Bonnet, but those would not correspond to a consistent theory of gravity, unless the couplings are small in some of these large parameters. And now the goal in this paper would be to work would be to study physics beyond 1/c. In other words, study loop diagrams in gravity, but studying them from the conformal field theory viewpoint, having a holographic CFD with these assumptions. And the question is, we would like to address this in a more general form. So we'd like to discuss generic holographic CFDs. For that reason, we'll have to consider operators that will be there anyway in all of those theories. And these are operators, obviously, that are made by the necessary requirement of having a stress tensor in the theory. So that means that we'll consider composite operators made out of the stress tensor. So these are multi-traces operators made out of stress tensor, and I might call this like double stress tensor or multiple stress tensor operators, meaning that they are generic multi-trace made out of 2 or more stress tensors. And here I have indicated the twist and the spin of those operators. Twist is generally the conformal dimension minus the spin, and this is what will characterize some power series expansion that we're going to discuss before. That's why I mentioned it here. So the objective would be to understand something about the presence of this operator as running inside in the OPE expansion of a conformal 2-point function, 4-point function. And what do we mean to understand? Basically to extract the OPE data of these operators to leading order 1/c, whatever term they contribute. So what we're going to do is which is the simplest way to address this problem, is to consider a specific 4-point function that's made out of 2 heavy operators and 2 light operators. And by heavy, I mean here that they have conformal dimension that scales with a central charge with this last parameter, and light, those that have of an order 1 conformal dimension. So we will want to study this correlation function, where I have also used the freedom of conformal invariance to set the points of 3 operators to be specific, infinity, 1, and 0. When this parameter is fixed, so indeed when the dimension of the heavy operator, it scales with C. And we will shortly see why this is useful. So there is another benefit besides obtaining this OPE data of studying this correlator, and this is that in the thermodynamic limit, we expect that this correlator will be roughly the thermal 2-point function of the light operator. And we know that by the ADS-CFT dictionary, the thermal 2-point function will be studied from fluctuations in a black hole geometry, ADS black hole, and therefore we expect that basically this heavy operator mimics the black hole state, and this study can give us some information about black hole physics. So in the dual gravitational description, the parameter that we are looking after, which was delta heavy over C that we want to keep more or less fixed, is, for example, in d equal to 4 dimension, what we will call mu in this talk, and it's proportional. It's basically the horizon radius in terms of the ADS radius. Now, to convince you a little bit more about how we'll manage these graphs and when they appear and why this study is a useful way of studying the presence of these operators, I'm looking at like this kind of 4-point function in terms of Witten diagrams that we're familiar from in gravity. And here I depict with 2 lines the heavy operator and 1 line the light operator. This is the order mu going to 0 result. So when we basically have just 2 disconnected 2-point functions for our 4-point function. Now at order mu at 1/c, we have a contribution coming from 1 graviton being exchanged between these 2 operators. And at order mu squared, this is an order magnitude higher, 1/c squared, we can have 2 graphs that are immediately loop graphs, as you see, when we have 2 gravitons exchanged this way or this way. And these are basically our double stress tensor operators running in between these 2 lines from the viewpoint of the CFT. That's not all the maybe diagrams that we know and would like to study, but these are the ones that will be classified by the presence of these extra stress tensor operators and from which we can extract some information. We are, of course, not going to study diagrams, we're going to study CFT, but this is a useful thing to keep in mind to understand why this expansion is useful and why studying this correlator is useful. So in general, this correlator can be studied in 2 limits analytically. This is the Regge limit that we're not going to discuss, and the Lycon limit that we're going to deal with. And this is when Z bar goes to 1 and Z is much, much smaller than 1, and the 2 points merge onto the Lycon. So the outline of the main subject of the talk will discuss a bit about the correlator, the results, and some summary and open questions. So we will study the correlation function in this limit, and although we wanted to keep this parameter mu fixed, we will have to do that or to study the correlator order by order in mu and hope that afterwards we can resum all the terms. And we'll focus below for simplicity in equal to 4 dimensions. Okay, so this is the correlation function that we're actually after, and any 4-point function in a conformal free theory is fixed by conformal invariance up to an overall function here of Z and Z bar. And the focus here will be to determine this order by order in this parameter mu. In principle, as I notice here, the multiple stress tensor contribute equally when this parameter is fixed, not just mu. So let's see how we're going to do the study. So we're going to use one of these or both of these two channels of OP expansions to study the correlator. One is when the light operators merge, and the other is when the heavy light operators merge. And this I will usually call S channel, and this I will call T channel. Here we have the presence of this double twist operators that are made of heavy light. And what happens in this S channel is that as we go orders by orders mu, they get more and more anomalous dimensions, contributions to their dimensions, and OPEs that come with or powers of mu. Here, however, in the T channel, we have new perhaps operators at order mu and at order mu squared, and so on and so forth. We have more and more operators. And since at order mu we have the stress energy tensor, we expect at higher orders we will have the presence of these multi-stress tensor operators. And so let's start with the study in the T channel. This is the expansion. This is the conformal, so in the OP expansion. So this is the conformal block. And here are the products of OP coefficients of heavy, light, of all the operators that contribute in the T channel. And they're classified by their spin and twist or spin and conformal dimension. So in the light cone limit, the T channel blocks behave this way. That's why we're taking the light cone limit when z bar goes to 1. And we see that exactly because of this reason, the operators with lowest twist will dominate the sum because of this behavior of the conformal blocks, where f is just some known function that depends, that's basically hypergeometric. So we're going to classify orders by orders mu by the lowest twist operators. At twist equal to 0, we have what operator? The identity. This is exactly the standard disconnected two-point function. And in the absence of additional symmetries, then we have the stress energy tensor whose product of OP coefficients is fixed by word identity to behave in this manner. And after that, in the absence again of extra symmetries over other operators, what we have is all these multi-stress tensor operators that are classified according to the twist and therefore contribute at different powers of mu. And the question is, how do we obtain their data? So evaluating the leading order contribution means that we have to compute their products of OP coefficients. And one can show basically, I don't have time to go over this, that they generally have this kind of structure at order mu squared. That means we're talking about this double stress tensor operators, and we have not included boxes here because the boxes will give us higher twist and therefore will be subleading in the light cone limit that we discussed. And these coefficients are basically given in terms of the spin of these multi-twist operators. So this was the main result of our paper. I don't have time to go through the details of how it was obtained. But there is also something else that you notice once you try to resum this whole series expansion to obtain the full order mu squared result of the correlator. Again, it's not a fixed mu result, but it's an order mu squared result. And for this already, we have to do an infinite sum. But we can actually do it. It's a sum of hypergeometrics. And what we get is this interesting expression. The following that this part is just fixed by conformal invariance and the limit we're taking. And what we notice is that we have a structure that's separated into 3 terms, where we have like f3 squared, f2, f4, and f1, f5, which are hypergeometric functions, or let's say the part of those that is characterizing the smallest twist conformal blocks. What the trivial observation is obviously that 3 plus 3, f3 squared is 6, 2 plus 4 is 6, 1 plus 5 is 6. And then the question is, what is 6 in this context? And this is something that's called the conformal spin. It's basically twist over 2 plus the spin and corresponds to the lowest spin operator of the leading twist family. So the leading twist family of operators here was this one. They all have the same twist for as many derivatives as you can insert. That's why we have to have an infinite sum for order mu squared. But there is like the smallest conformal spin that you can have, and that corresponds to the case where you have no derivatives in between and just the two t's. Okay, so this is the operator that has conformal spin 6. Is the lowest spin operator in that class, and this is the one that gives us this number 6, for which determines the structure that we see here. Now we were able to go beyond that and compute OP coefficients for these operators at order mu cube. So if I want to give you like a few words about how to do this computation with you, what we did is we understood that there will be a structure of this type. And for order mu squared, of course, we have like F3 cube and therefore have higher conformal spin. And we could add many, many more structures. Then we checked which of those are independent. Unfortunately, not all of them were independent, but that we could exclude one. And then we were able, by matching with the S channel, to obtain the appropriate numbers here and fix completely this order mu cube result. So, so this is one thing, one take-home message, that although this seems like a good trick, good ansatz to work with, not all of these functions are independent from each other. And there is another thing here that I noticed, and this has to do with the fact that all these numbers here that you see that contribute to the point function seem to diverge at specific values of delta light, integer values. And this has to do with the presence of extra operators, which will have exactly the same twist with those of the multi-stress tensors that we consider, and therefore in reality this result is not valid for those cases, but one would have to solve a mixing problem with the contribution of this kind of operators, which are let's say multi-twist operators that are composed out of the light field. So what is very intriguing about this is that the structure that we find here at each order in mu, and we have actually checked that it happens at each order in mu, so these ansatz we can make out actually correctly solves for our correlation function at each order in mu, is very similar to the structure that one finds in the 2D Virasoro vacuum block that describes the classical physics in gravity. This is the full result for the correlator is known for some time. And we had observed that there the structure was of this form at order mu, if you expand this function, where basically F2 gives you the global block of the stress tensor operator in 2 dimensions now, as opposed to 4 dimensions that we were using before. This is, of course, not quite what we're having. We have F2, and while we would like to make something made out of F3, which is the block that corresponds to the stress tensor in 4 dimensions, and there it comes to mind that basically this would appear in 2 dimensions as a spin 3 card. And we know how to deal with higher spin theories in 2 dimensions. We know how to add a spin 3 current in Virasoro, and the vacuum block in those cases has been computed, and it's a similar 4-point function. Its structure is much more complicated and depends both on the conformal weight of the heavy operator and the charge of the heavy operator and the charges and conformal weights of the light operators. But we can take a specific limit where we scale this to 0. So now the heavy operator is characterized by a heavy spin 3 charge, not by heavy conformal dimension, and relate the conformal dimension and the spin 3 charge of the light operator in this form. Then the block of spin 3 exponentiates and has a similar expansion that's made out of indeed F3, F2, F4. However, we see that there is some difference from the result that we were hoping to obtain in 4 dimensions. And here we see that we only have 2 structures, while we had 3 structures in the 4-dimensional case. We had a term which would behave like F1, F5. Here it's absent. And similar issues show up in higher dimensions. So it's not the spin 3 block that we could describe our 4D light cone 4-point
Just
function.
you have
Yes.
6 minutes now.
I have still 6 minutes. Yes.
Yes.
Okay. Thank you. Thank you.
Including question.
Yes. Thank you. So, but we went close. So there are like other interesting questions that pop up because of the structure that is present here. The question is there some new algebra that would describe this higher dimensional, this 4-dimensional CFT 4-point function, and that would fix its structure? Unfortunately, these are not the correct basis because they're not independent functions. And people have searched for something like that, especially describing the light cone limit of these correlators in 4D, for example, and higher D, by looking at Anek operators or some generalization of Anek operators, which would mimic some sort of the Virasoro. And they act indeed like annihilation creation operators on the vacuum. They form on orthogonal basis when the transverse phase directions are 0, and one can actually compute the commutator of these two generalized Anek operators for m and minus m, and one finds like a structure of this form, which is unfortunately divergent, can be regularized, and if regularized, it will give us the correct central charge term for an algebra that would describe what we have. However, if you go beyond this and you want to fully compute this commutator, you see that it is either not consistent, or basically you can't really resolve the divergences that show up, and also it doesn't give the answer that we are after. So it wouldn't be the right answer to describe the light cone limit. So let me summarize what we have here. So we studied the stress tensor sector, so only how the multi-stress tensor operators contribute to this heavy light 4-point function. These are always present, but they might not give the dominant contribution in the light cone limit for holographic CFTs with many other operators which may have lower twist. Order by ordering mu, we saw that there is an expansion that can be characterized by these different f functions. We also noticed that this correlator exponentiates, and by exponentiates we mean precisely this, that it is given by delta L times f, and f has this expansion whose coefficients behave like order 1 when delta goes to infinity. And again, this is given by products of FA functions that we saw before. And we have shown, so in practice, what we have shown for our claim is we couldn't deal with an infinite corrections to order mu, but we could show that it works in principle for several, up to order mu to the 6, determined OP coefficients using this ansatz, solved the bootstrap and stuff. We also have computed all of them, the Lorentzian inversion formula at order mu cube. And then we noticed that there are some dissimilarity between even and non-dimensionality of space. When we have even dimensions, these ideas seem to easily be generalizable and work, for example, in 6 dimensions. But for all dimensionality, even for d equal to 3 CFTs, we can't really use this particular ansatz. You can immediately think of this because these f functions will be characterized by half-integer numbers, and how to make out products and whether this product n is not completely clear. Moreover, these are not simple algebraic functions, while here all these hypergeometrics reduce to simple algebraic functions without log. So there are many questions, but here I will leave that to what happens beyond the light cone limit in view of the time. Similar things work out actually. But there are several questions besides the ones I've already mentioned, is indeed what underlies the structure, whether we can access this algebra that seems to be there, whether we can resum the series and find the result for all orders in mu, just like we do in 2D, and for that the algebra might be a way to go. And then what happens when delta is an integer, and even more important questions once we resum all this, whether there are interesting questions to ask about black hole physics and the light cone limit for this correlation function. So thank you for your attention, and
Thank you for that nice talk. We will have some time for questions. Is there any question from the audience here?
hello.
Okay. Are there online questions? Okay. So if there are no questions, let's thank Manuela.
Thank you.
Thank you.
Hi, Sanjay.
Hello, Manuela.
Hello. So I should stop
Next
sharing
topic,
my screen. No?
Sanjay, you're there?
I am here. Yeah.
Okay, could you share your screen with us as well?
Yeah. Let's see.
Okay, so the format, as I don't know if you heard me earlier, is 25 minutes of talk plus 5 minutes questions. Okay.
Okay.
I'll give you a warning just 6 or 7 minutes before the end. So our next speaker is Sanjaye Ramgoolam, and he's going to tell us about string theory, random tensors, and combinatoric constructibility. Go ahead, please.
Great. Good morning, and everyone, and thank you for the invitation to the organizers. So I'll be talking about string theory, random tensors, and combinatoric constructibility. This is based on a series of papers with Joseph Benjeloun, the first one in 2013, another one in 17, and a more recent one. Let's see. So in string theory, we are interested in maps from the worldsheet to space-time. So you have some worldsheet existing in space-time, and we think abstractly about the worldsheet as a separate entity, and we have a map from the worldsheet to space-time, and this is the map, and we want to study the dynamics of that map. In topological string theories, very often all the partition functions and observables are computed by localizing to an interesting subspace of the space of all maps, for example, holomorphic maps satisfying an equation of this form. So in gauge string duality, one of the great discoveries of string theory in the last several years is gauge string duality, which says that a string theory of the kind that I just described, the theory of maps from worldsheets, can have an equivalent description in terms of another physical system, which does not obviously look like a string theory. So, for example, we have the old matrix models discovered around the late 80s, early 90s, where the dual physical system is defined by integration of matrix variables. In this case, you have a theory of matrix integration, so effectively a zero-dimensional quantum field theory, and the string theory lives in one dimension or less, in an appropriate sense, one or less. And another example of such gauge string duality is two-dimensional Yang-Mills theory with UN gauge group. When you do the large N expansion of that and you look at what is happening at each odd n 1 over n, and you discover at each odd n 1 over n, this theory is counting maps from worldsheets into the target space where the Yang-Mills theory is defined. And another example of very important example of gauge string duality is the ADS-CFT correspondence, of course, where you have 10D string theory, for example, being dual to four-dimensional gauge theory. So I will be starting the talk by thinking about the complex matrix model, where I have complex variables, complex matrix variables of size n. That's going to be the partition function, and the measure and the action are invariant in the UN, and Z transforms in the adjoint of UN. And physically interesting observables are UN invariant, gauge invariant polynomials made out of Z and Z bar. And we're interested in doing integrals of such invariants. And so what we will find, and what I'll review, is that this complex matrix model, well, I won't really review much, but this complex matrix model is an important sector of ADS-CFT correspondence. And another thing which would play a more important role within this talk is that within this theory for certain class of observables, this provides a beautiful example of lower dimensional gauge string duality involving maps from world sheets to some target space. So just by looking at this matrix model and you look at the observables, there is you can see maps from world sheets to target space. So I will talk about that, complex matrix models, along with the appropriate maps. And a special kind of maps appears called belly maps. And these are related to combinatoric structure called bipartite graphs. Now, other aspects of the complex matrix model encourage us, motivate the organization of the observables using Young diagrams. So within the complex matrix model, we're looking at both bipartite graphs, an interesting combinatoric structure, and Young diagrams. This story generalizes when we go to complex tensor models. Again, the same kinds of belly maps appear, somehow in a different way. Here, the belly maps and bipartite graphs, the belly maps appear in describing correlators. Here, the belly maps appear simply in describing what the observables are. So that's what happens in complex tensor models. So in the question of enumerating observables, you get belly maps or equivalently an associated combinatoric structure of bipartite graphs. And when you go to this other side where you explore the analog of Young diagram description of observables, here you get triples of Young diagrams. And these triples of Young diagrams naturally come weighted with Kronecker coefficients, which I'll tell you more about soon. And by exploiting the fact that bipartite graphs and Kronecker coefficients appear together within complex tensor models, we are led to develop a lattice algorithm for Kronecker coefficients, which I'll explain is an interesting question for mathematics and combinatorics. So in the complex matrix model, we have, this is our partition function. Holomorphic gauge invariant things are the things of interest here. So you have this holomorphic thing and the anti-holomorphic thing. And we just want to understand general integrals of this form. We divide it by the partition function. That's our correlator. And we can calculate such things using Wick's theorem, for example. So first, we need to think about the space of these observables. So you can organize these invariants by their degree. And degree 3, for example, we have degree 3 polynomial invariants of one complex matrix. So you have things like trace Z cube, trace Z squared, trace Z, or trace Z the whole cube. So traces and multi-traces. And when the size of the matrix is bigger than 3, with the degree that you're thinking about, all these are linearly independent. Otherwise, things become dependent, and that can be described using Young diagrams. But for a lot of what I'll talk about, large N is going to be important. So we're looking at the combinatorics of these different ways of putting your matrix inside a trace, which is related to partitions. You're splitting the 3 into different into single traces or multi-traces. So this is a problem of partitions. The 3 is either equal to 3 or 2 plus 1 or 1 plus 1 plus 1. And for each such partition, there's a trace. Now, P of n, the number of partitions, is also the number of conjugacy classes in the symmetric group Sn. The fact that traces are related to conjugacy classes is not an accident. It's you can actually parameterize your gauge invariance using permutations. For example, trace Z the whole square is just this object. Trace Z square is where these indices are contracted in a different way. So that's Z square. This is contracted here. So fixing and ordering of the upper indices there are different orderings of the lower indices, which leads to different traces. And these different orderings correspond to different permutations. And this is a general story because for any degree, you just write gauge invariance by having z's with indices summed. And if I name the top indices I1 to In in a fixed order, then I can contract the lower indices because everything is gauge invariant. The same indices must appear below, but in any possible order, and there is an observable for every permutation. Because these are bosonic variables, you can move the z's around. This observable that depends on sigma is actually the same as the observable when I conjugate sigma. Sigma goes to gamma, sigma gamma inverse conjugated. So this permutation of z's is described itself by gamma. So great. So we've learned that the degree n invariant polynomials are related to the number of partitions of n, number of conjugacy classes of Sn, and also this is related to the dimension of an algebra, the dimension of the center of the group algebra of Sn. So it is useful in describing the correlators to think about different permutations in the same conjugacy class. So you fix a trace structure and you think about the sum of permutations in that conjugacy class for that partition. You sum them all up and divide by the number of elements in that conjugacy class. That's another way to describe your multi-trace operator, which is given by a certain number of traces, number of traces of z squared, and so on. So these permutations are useful because they also tell us about the correlators, and it'll be useful to define this function on the group of permutations where delta of sigma is 1, if sigma is the identity, and 0 otherwise. So using this delta and using these permutations, there's a neat formula for the correlators that I described before. So if you take this observable, your multi-trace operator, and another one which is anti-holomorphic, what is the two-point function? You just sum over all the permutations in the first conjugacy class, and you sum over permutations in the second conjugacy class, and then you sum over permutations in all permutations in Sn, and there's a weight which is this delta function, and n to the power of the number of cycles in that. That's the answer. Okay, so observables are described by these permutations, and they are useful in order to describe the complete large n expansion of this correlator. And what appears in that large n expansion is sums over permutations constrained to multiply to 1. Okay, and this simplifies at large n, and the 1 over n corrections are all here. So what is this thing? So this just comes from doing your Wick contraction combinatorics, and then you get this answer. This has a very nice geometrical interpretation. It is also the sum of maps from a world sheet, from a surface to a sphere with 3 branch points. And these branch points, the structure of these branch points is described by conjugacy classes. This is the kind of thing that was very useful in 2D Yang-Mills. And then it also comes up simply in the complex matrix model. So we have holomorphic maps from a world sheet to a target. And generically, these maps have degree n. But at special points on the target space, the inverse image has fewer points. And the structure of these inverse images is described by those conjugacy classes. And because there are 3 such conjugacy classes, it's a space with 3, it's a map with 3 branch points. And you can also write down the genus of the covering surface of the world sheet using the cycle structures of these 3 permutations. And it turns out that world sheet maps, which are holomorphic and have exactly 3 branch points, they have a special role in number theory. They're called belly maps. It is known that such maps can be written using some equations for the curve and some equations for the map. And these equations will involve some indeterminates, x, y, z, and some coefficients. These coefficients can be restricted to be strictly within algebraic numbers, the set of algebraic numbers. And so for that reason, these 3 branch point maps are very well studied. And they're related, as I will say later, to graphs that I'll describe. So all this interesting stuff, that summing over permutations you can do within just purely the group algebra, which is sum of permutations. And within the group algebra of Sn, there are these guys which are central elements. They commute with everything. This correlator can also be described in terms of these central elements. And basically, these central elements define a subalgebra of this group algebra. So within this correlators business, there's an interesting algebra. And as I mentioned, if you take large powers of Z, these traces are no longer independent. Rather, they are linear dependencies. Traces can be rewritten in terms of products of traces. And then to get a nice linear basis for the invariants, we go to Young diagrams with no more than n, capital N rows, where capital N is the size of the matrix. Corresponding to each Young diagram, there is an invariant operator. So you take these sigma operators, you sum them using characters. And turns out that the matrix model gives you a nice inner product, and these are coming from with contractions, and these Young diagram operators are orthogonal in that inner product. So basically, though, what is happening is this algebra, the algebra which is the center of the symmetric group algebra. And in this algebra, there are two bases. One is the one related to conjugacy classes, which I talked about, averages over conjugacy classes. But then you can change basis from there to get things labeled by Young diagrams, and the change of basis is given by characters of Sn. So the summary is that inside the complex matrix model, a lot of the structure, correlators, and so on are related to this algebra, the center of the group algebra. And there is two bases, conjugacy classes and Young diagram basis. So, so all of this story has an interesting generalization to tensor models. We still have algebras related to the group algebra of Sn. And there's a Fourier transform which relates to different kinds of bases, which is important. So you have here in the complex tensor model, which has been studied in the quantum gravity literature and more recently in the string literature as well. Take a tensor Zijk, complex Z bar Ijk. They transform in the fundamental of UN cross UN cross UN. And you have Z bar Ijk. This is the partition function. Here, the invariants must contain, each invariant must contain Z and Z bar, because the Z's are in the fundamentals and the Z bars in the anti-fundamentals. So you have things containing Z's and Z bars, which must be contracted in some way. And then you can compute the one-point functions, which is the simplest thing to think about. So each of these Z's, sorry, I'm calling it phi here. The Z has a 3 index. You can associate to it a triple of just a vertex with 3 kinds of legs, colors IJK, red, black, blue, and red. Phi bar has these kinds of things. And the contracted things come from drawing graphs. So this identification of I with I corresponds to this identification, J with this one, and so on. So for a general observable made out of n copies of Z and n copies of Z bar, again, you're going to have contractions. Because we are looking at invariants which are separately invariant under the UN cross UN cross UN, separately, the first indices must be contracted with the first indices, the second index, the list of second indices with the list of second indices, and the third with the third. And each of these set of first index contractions is parameterized by a permutation sigma 1, second index contraction sigma 2, third index contraction sigma 3. So you can build any invariant of degree n by taking 3 permutations in the symmetric group Sn. And as before, there is an identification in the sense that not all triples give you distinct operators, because you can move these around by a permutation, move these around by a permutation. So there is an equivalence. If you multiply your permutations simultaneously on the left by 1 permutation for moving the Zs, simultaneously on the right by another permutation moving the Z bars, you get the same observable. So this defines, so we're therefore looking at triples of permutations modulo a diagonal action on the right and a diagonal action on the left. This double coset has an algebra structure associated with it, which I'll tell you more about shortly. So we're thinking about these triples of permutations related to observables. There's this equivalence class. You can do a little gauge fixing because there are 2 gauge degrees of freedom. You fix one of them. And after you do that fixing, you have just 2 permutations parameterizing your observables. And then there's a remaining equivalence, which is just 1 permutation. And that's just simultaneous conjugation. So it's a bit like conjugacy classes, but you're simultaneously conjugating both with the same permutation. So after doing this gauge fixing, you have pairs of permutations subject to this simultaneous conjugation. And this structure is related to bipartite ribbon graphs embedded on a surface. Okay, just graphs, edges and vertices embedded on a surface. There's some technical definitions. For example, if you're given a pair of permutations in S3, the identity and identity, the vertices are labeled. So you have a bunch of vertices, 3 of them for degree 3. And then the edges are labeled 1 to 3. And identity means that as you go around, following the orientation of the surface, you go from 1 to 1, 2 to 2, 3 to 3, and so on. And then if you have a permutation 1 to 3, you have a vertex with 3 edges in this way. And the order of these, the precise permutation matters because 1 to 3 and 1, 3, 2 are different. When you switch one of them, you get a different graph because the orientation matters. So embedded graphs correspond to these pairs of permutations subject to that equivalence. And related to these pairs of permutations, you can multiply them to get a third one. So it's related in turn to belly maps of the kind of thing. This is the kind of thing that came up in complex matrix models. So the upshot is that we have pair of permutations subject to this simultaneous conjugacy class. This is a group action on a set, and the set is itself a pair of permutations. So you have orbits of the group action. So we have the number, therefore, for fixed n, we have an interesting number, which is the number of ribbon graphs, which is the number of orbits of the simultaneous action, and which is the number of belly maps and the number of ribbon graphs. For each of these orbits, so you take a pair of permutations, you list distinct orbits, just like you list the distinct conjugacy classes. Here are the pairs of permutations. Simultaneous conjugation generates something which is kind of analogous to a conjugacy class element I talked about before. So these averages, they span a subspace of the pair of Sn cross Sn group algebra, and that subspace is called K of n, which is also a subalgebra. And basically, there is an interesting algebra which has a dimension you can calculate, and you can calculate it in 2 ways. One of them having to do with partitions, one of them having to do with Young diagrams. When you do it with partitions, you get a sum over partitions with the symmetry factor of the partition. Young diagrams, you get some triples of Young diagrams with the canonical coefficients. The canonical coefficient is just the number of invariants, the number of one-dimensional reps in the tensor product of these 3. So this gives a very interesting kind of way to think about canonical coefficients. The sum of the squares of them is related to the number of ribbon graphs. Okay, so which is a very nice combinatoric structure, number of ribbon graphs. You can draw them. Now, in canonical coefficients are very interesting because there's a question, is there some way of kind of constructing them? So in symmetric group representation theory, lots of things like Littlewood-Richardson coefficients, tensor products of UN things, Young diagrams. You can put together Young boxes of a Young diagram according to some rule, and the number of ways you do that leads to the Littlewood-Richardson coefficient. There's no obvious direct way of doing that for general triples when you come to the canonical coefficients. So that's the constructibility question. You have formulas, of course, for it involving characters, which involve pluses and minuses. These characters can be positive or negative. So is there a manifestly positive construction? So here we have a hint that the sum of squares of C have a nice construction simply in terms of ribbon graphs. So can you specialize this? So we looked at this question in the latest couple of papers. So the sum of squares is constructible in terms of ribbon graphs. What about a particular canonical coefficient? So to do that, you look more deeply at this algebra K of n, which has a basis. On the one hand, it has a basis labeled by these ribbon graphs. On the other hand, it should have another dual basis, analogous to the projectors I talked about before. So there is actually a basis labeled by triples of Young diagrams, and for each triple, the number of these guys is the number of the square of the Kronecker coefficient. And you can write this using group theory. Instead of characters, for projectors, we had characters. Now you have matrix elements, and you have, so you take a triple of Young diagrams, and you take a pair of permutations. You sum over them with the matrix elements in the two representations. And then you take some Clebsch-Gordon coefficients that couple these two representations to a third one. That's how three representations come in. And when you do such a thing, there's a multiplicity coefficient. So the number of these will be the square. That's a multiplicity, which is the number of invariants in R1 tensor, R2 tensor, R3. So that is a basis you can write down. So it turns out that there's another way to think about these Qs, which doesn't actually involve working all these things out in detail. Rather, it involves solving an eigenvalue equation, some eigenvalue equations. What the eigenvalue equation does, it picks up, sort of identifies these three Young diagrams. So we have, so we want to identify these three Young diagrams, because once we have identified them, the number of states left is going to be the Kronecker square. So you can identify these Young diagrams by using left multiplication by the group algebra elements. And the eigenvalues of this left multiplication are the characters, normalized characters. And if you...
sorry to interrupt, you have about 6 minutes now, okay?
Okay, great. So when turns out that to identify things to identify Young diagrams, it suffices to take the conjugacy classes of, permutations with a single 2-cycle, a single 3-cycle, up to some cutoff k, which is actually less than n. And numerically, you can investigate this. So just by taking single cycle permutations and the associated conjugacy classes, their list of characters, you can identify Young diagrams. So using that identification, using these class operators, you have some eigenvalues equations for these Qs and some left multiplication by these cycle operators. There are three ways to multiply. Either you multiply on the left slot or the right slot, or simultaneously on both slots. So you get three kinds of operators. So you get these three kinds of operators, which leads to a system, an eigenvalue system for these Qs. And this eigenvalue system, basically now, you can set it up entirely in the geometrical basis, which was associated with those ribbon graphs. So there was something in terms of a sum of permutations entirely labeled by the ribbon graphs. So one for each ribbon graph. So these cycle operators, you multiply them and you get some integer matrices having to do with how you multiply, how these ribbon graphs mix when you multiply. And so you get some integer matrices, and this eigenvalue equation, you can set it up as a matrix equation. And if you know the eigenvalues, which you know because they're normalized characters, you can set up a null vector equation. And this null vector equation involves just integer quantities, which are these integer matrices for multiplication, and the integer characters that I told you about. Those characters, it turns out, are integers. So the upshot is that you have an integer matrix that depends on a triple of Young diagrams, and you're looking for its null vectors in a space spanned by ribbon graphs. And this kind of null vector problem for integer matrices is a very combinatoric problem. You can do it. It has to do with multiplying the rows of the matrix, shuffling them around, and it can be done combinatorially. So the upshot is that we're looking at lattice of ribbon graphs, which is a linear combination with integer coefficients. And within this lattice, you have the solutions of that eigenvalue problem. And the eigenvalue problem depends on a triple of Young diagrams. So within the space of linear combinations of all ribbon graphs, which is this is the number of ribbon graphs. Within that, there's the integer linear combinations. And there is a subspace labeled by triples of Young diagrams. And you look at the integer part of that, the integer solutions, and you'll get a set of integer vectors within this sublattice, and you count them, you're going to get the square of the number of Kronecker coefficients. So that's a kind of a lattice algorithm for calculating, which just comes from an eigenvalue problem. And this algebra that I talked about is also a Hilbert space. There's an inner product on it, and is TKI a Hermitian operator. So all of this problem can be set up as a question having to do with the eigenspace of a Hamiltonian. And as a result, one can use techniques. This is a future direction from quantum computing, where these large matrix problems, you can approach them and get some speed up using quantum algorithms. So that's a future direction. So there's a membrane interpretation to this quantum mechanics, because these ribbon graphs correspond to surfaces, and then now in this quantum mechanics, you're time evolving these surfaces. So as the surface evolves, it specifies a membrane world volume. There's a quantum membrane interpretation. Given the time, I won't explain it in detail. There's a couple of open questions, and I'll just leave this here and entertain any questions you may have.
Okay, the floor is open for questions. Yes, please go ahead.
The mathematics of for real application, par exemple, for
I think we lost the sound. Sorry, I'm not hearing the question. Don't know if it's a problem my end.
I also don't hear. I'm made the host, Sanjay, sorry. I mean, I can hear you, but I don't hear anybody else responding. I don't see anybody else, I think.
Oh, yeah, I see some people on the right as participants, but I'm not hearing the question.
Yeah, so yeah, I think the Corfu, the organizer's Zoom is not connected anymore, I think.
Ah, I see. Yeah, that's true. Yes, I see a number of participants, but yeah, the organizer Zoom seems to have dropped. Or maybe give it a minute and then see.
Yeah, so they're okay. They're coming back.
Ah, okay.
I think I see. Hello, we had lost you for a while. Can Sanjay start?
Yeah, no, so I was just entertaining questions. So any questions?
They are the host now, so in principle they can respond, but maybe they don't hear well. But
yeah, I think the host was Nair, right?
Okay.
Oh, hello.
Oh, okay, Sanjay. So the question was, could you comment on use of ON symmetry rather than UN in what you were doing? And
okay. So I think for ON symmetry, there is a similar story, and in fact, in a separate paper by Joseph, he has explored that. The basic story, the basic structure is similar. You know, you can parameterize the key point was that the set of invariants could be parameterized using permutations. So with ON, the diagram you draw here is going to be a little bit different. You're going to get some Zs, if you like. There's no distinction between Zs and Z bars. It's just a bunch of Zs. So you're going to get some things like this on a single row. And then there's going to be some contraction, and the contraction, again, can be parameterized by permutation. The equivalences that you get on the permutations are different. But again, the story, the key element of the story is that there is a description of that space of invariance using something combinatoric having to do with these graphs that we just talked about. And there's kind of, after Fourier transforming, there's something having to do with Young diagrams. So I believe there is a formula of this sort. I forget the details of exactly the form of what appears, but it's a little bit different from that. Not sure the algebra itself has been identified, but certainly a counting formula of this form is known. And so at that level, up to this level, I'm pretty sure similar things are known. And I think the description of the algebra, I don't think there's a clear description of exactly what the algebra, sort of closed algebra is. But I think that should be something where progress can be made.
Are there other questions? Let's check online as well. So if there are no further questions, let's thank the speaker again.
Thank you very much.
Thank you. And our next speaker is Roberto Percacci from CISA. And we have to take a moment to set it up, I guess. Okay, the title, as you can see, is High Derivative and Metric-Affine Gravity. So first of all, many thanks to the organizers for organizing and for inviting me. I'm going to talk about some well-known theories, high derivative gravity and metric-affine gravity. These theories are so rich that there's really a lot still to be discovered here. What I'm going to say is based in part on work with Evgeny Skvortsov, Kevin Falls, Nobuyoshi Ota, Alessio Baldazzi, and Luca Zambelli. For high derivative gravity, or more precisely four derivative gravity, is the metric theory of gravity, where the action contains terms linear and quadratic in curvature. So here I organize the quadratic terms into the Weil tensor square, Ricci scalar squared, and the density of the Euler invariant. And note that I call Zn the inverse of Newton's coupling. So the basic quantum properties of this theory are well known for a long time, but really more is needed to understand exactly what goes on. Metric-affine gravity, on the other hand, is a theory where the connection is treated as an independent variable. And the simplest and best known version of this is Palatini theory.
But in Palatini theory, the connection is frozen by the equations of motion. I'm interested in the case where the connection is a propagating degree of freedom. And for that, you have to go to terms beyond linear and curvature. So I'm interested in metric-affine gravities with propagating torsion and non-metricity. So the main reason for studying metric-affine gravity is that it makes gravity much more similar to the theories of the other interactions that we know, and that I think is a necessary step towards unification. But even without that, I'm not going to talk about that, but I will also show that in some sense this theory is superior in some ways. Now, quantum properties of metric-affine gravity are basically virgin territory. I'm not aware of much work on this. So let me start by recalling some old results on high derivative gravity. So it propagates a single graviton, and then there are a spin 2 ghost and a massive spin 0 mode. Now, depending on the signs of the couplings, these may also be tachyons. And we try to avoid that. So we have to fix lambda inside to have certain signs. So Kelly-Stell showed that this theory in the presence of the Weyl square term is renormalizable. But then it turns out that there is no choice of parameters for which the theory is simultaneously renormalizable and unitary. And basically, I think this is the reason that motivated string theory. This makes this theory not immediately viable as a quantum theory of gravity. The other well-known property of these theories are the beta functions of the high derivative couplings, lambda, psi, and rho. They were calculated in the 80s. And, well, depending again on the signs of these, but the theory may be is asymptotically free if lambda is positive and psi is positive. So if the theory is asymptotically free, in some sense, it's as good as QCD. It's an ultraviolet complete theory. So these beta functions were subsequently rederived using non-perturbative functional renormalization group. This is where I was involved. So this non-perturbative or functional or exact renormalization group equation is just a way of implementing Wilson's idea of integrating out modes one shell at a time. And I write here this functional equation in a very vague form. One defines a scale-dependent effective action gamma sub k. So for k equal to 0, this is just the usual effective action. But then there's a dependence on this cutoff parameter k, which is introduced as an infrared cutoff really in the functional integral. And then from by some formal manipulation from the functional integral, you can derive an equation for the derivative of gamma with respect to k. And I write it in this rather vague form where it is just a trace of some function of some differential operator. I don't enter into details. But I show it here in this way because it has a striking similarity to the formula for the spectral action, which is used in noncommutative geometry. And I suspect that this, and then in order to compute the right-hand side, both in spectral geometry and in this equation, one just uses the heat kernel and expands the right-hand side in powers of curvature. And the coefficients of the expansion are the momenta of the function W. So I suspect that, in fact, this methodological similarity really hides some deeper connection. But I just say it here because there's an audience that may be sensitive to these issues. What you do with this, so even though the gamma defined from the functional integral is ill-defined, this equation here is perfectly regular, both ultraviolet and infrared. And you can take it as a basic definition of the theory. you start, and then you just integrate this gamma from some initial condition down to k equal to 0, and you can calculate the effective action in this way. Anyway, from here you can obtain beta functions, and so if you insert here instead of gamma the formula for the action of the high derivative gravity, you obtain beta functions for all the couplings. And if I expand to first order in Z, the beta functions that you get are these. And you see that the first term here are exactly the ones that were derived by Abramidi-Barvinsky in perturbation theory. And then there are corrections proportional to Z. And then there's also beta functions for Z here. You can solve these and you get various fixed points. The first one is the perturbative fixed point where lambda and psi are asymptotically free, and G has some non-trivial value and also cosmological term if you want. And then there are other couple fixed points here with where all couplings are non-trivial. So when you see, then there are actually more, but that I didn't even show. So you can ask here, what is the relation of these to the perturbative study, and should we trust these fixed points, and so on? Or can one flow from, for example, from any of these fixed points towards the Gaussian fixed point of perturbative Einstein theory, where you expand in small g? It's not clear. The answer is not known. One can try to, partial answers can be obtained by looking at the dependence of these results on the regulator. In the definition of gamma k, one puts this suppression factor in the propagator. This propagates, so this is momentum, and you suppress low momentum modes. As I said, this your gamma k is defined by some infrared cutoff. And this scale here is k. Now, it turns out that one can reproduce the results of dimensional regularization and MS bar from the functional renormalization group by taking a particular limit in this regulator. It's the limit in which you suppress the regulator. You put it you put a prefactor A in front of it, and you let A goes to 0. So you just uniformly suppress it. I would call this the limit of vanishing regulators. And then in this limit, when A goes to 0, it turns out that the fixed point 1 it has a really perfectly good limit. It's really in the sense that the scaling exponents remain basically constant all the way. The other two, FP2, FP3, are really suspect, and work is underway to understand whether they are robust or not. And other fixed points disappear even earlier. So, however, in all cases, it's important to note that G goes like 1 over A log A. So if you take this limit of vanishing regulator, the fixed point for G goes to infinity. So a fixed point for G goes to infinity, it means that, remember that the action contains 1 over G. So it means that the Hilbert action disappears from the, well, it has a vanishing coefficient, so it's no longer there. So you are just with pure high derivative gravity. And in this sense, you reproduce the perturbative results that you can get from dimensional regularization. Because in dim reg, you don't see any fixed point for Newton coupling. And here you can see that the reason that you don't see it is that it's just at infinity. Okay, so I think that's all I wanted to say about high derivative gravity. Let me come to metric-affine gravity. So my basic notation is this. I use for the of course there's a Levi-Civita connection in the theory because there's a metric, and I use for it the standard notation of general relativity. So the connection is called gamma, the covariant derivative is nabla, and its curvature is Riemann tensor, and it's called R. And then there's a dynamical connection, and for that I use Yang-Mills terminology, Yang-Mills notation. the connection is called A, the covariant derivative is D, and its curvature is called F. Now, the new ingredient in gravity relative to Young-Mills is the frame field. So given if the metric in coordinates has components g mu nu, then the components of the metric relative to the frame are GAB and are related to g mu nu like that. This frame is just looks like just a gauge transformation. And now, if this were an orthonormal frame, this would be 8IB, but I don't assume that. So GAB here is a bunch of scalar functions on space-time. I'm going to use the same name for a geometrical object in any frame because you know, it's just components of the same objects in different frames don't deserve different names. So G is here G mu nu, and the same G there GAB. And also for the connection, there's a connection with Latin indices A mu AB. Sometimes it's called spin connection, and maybe another name is used, but really it's the same object in different frames. Now, the other important thing is that the difference between A and gamma is a field phi. And by the way, if anybody knows a good name for this tensor, please tell me, because it's a very important object, and it doesn't. I haven't found any good name in the literature for that. So difference between the independent connection and the Levitshev connection, which is determined by the metric or the frame. So you can present this theory in two ways. One is to write the action as a function of the metric and the connection. I call this a Cartan viewpoint. The other point of view is the following. You have G here, so with G we can construct gamma, and then you can replace A by gamma plus phi. And then you can rewrite the action as a function of G and phi. It's just change of variable. This new type of description I call Einstein point of view. Well, here they are. This is the relation. It's just frame transformation, just change of frame. Now, what are torsion on metricity? You have in a generic linear frame, torsion is the covariant exterior derivative of the frame. Non-metricity is defined as the covariant derivative of this metric here, GAB. So you see, both involve covariant derivatives of some field here. And these fields, theta and G, carry nonlinear realization of the linear group. And therefore, later on, I'm going to call them Gaussian bosons in quotes. Now, if you decide to work with coordinate frames, you can do that. That means that you set the frame components to delta A mu, and then the torsion becomes just an algebraic combination of the connection components, whereas Q still contains derivative of G. Conversely, if you decide to work with orthonormal frames that you can do, then it is a torsion that contains derivatives of the Gaussian boson, and Q becomes just an algebraic linear combination of A's. So I'm saying this because very often in the literature you find a theory described just in one of these two frames, and then things look different depending on how you present things, what frames you choose. These are just gauge choices, so physics cannot depend on it. But you see that sometimes there are derivatives, sometimes there are no derivatives, and so it may be confusing.
Just one question, but in your action, there is a dependence on the frame.
The action is constructed with invariance, and the invariance you can write in any basis you like, right? So metric-affine gravity contains higher derivative gravity. If you insert, so a typical Lagrangian for metric-affine gravity will contain terms linear and quadratic in F. And if you use this split, F becomes a Riemann plus covariant derivative of phi plus phi square. So a Lagrangian like this becomes terms with Riemann, linear in the Riemann tensor, quadratic in the Riemann tensor, and then there are other terms that involve phi and derivatives of phi and the Riemann tensor. So you see that if you write this metric-affine gravity Lagrangian in the Einstein formalism, it will just look like metric-affine gravity plus some funny matter field, which is a cleaned extensor phi. I will write it here a little more explicitly. The Lagrangian will contain here. The first line are dimension 2 operators, the curvature and phi square. The second term contains terms that are bilinear in the field, so r square gradient phi square, which is a kinetic term for phi, and r gradient phi. So these only contribute to the 2-point function of phi and of the graviton. And the third line contains terms of the type r phi square, cubic interaction of phi, and quartic interactions of phi. So those are vertices. And I'm going to talk mostly about these 2-point functions. Now, counting. Now, even writing the Lagrangian is complicated, especially in the Cartan formalism. You have many invariances you can write, but there are also many relations between them. They are not independent. And so writing the independent invariants in the Cartan formalism is already a headache. So it's easier really to write things in the Einstein formalism. Then you can count these invariants more easily. And these are the number. So there are 11 mass terms for phi. There's only one Palatini term, one Hilbert term. There are 3 r squared terms that I showed earlier. 38 possible terms with nabla phi squared, and 12 terms of the type r nabla phi, and many interactions. If you use Bianchi identities, this number 12 goes down to 6. But still, there's a rather large number of invariants already just in the 2-point function. If you use Bianchi identities, probably you can reduce some of these numbers a little bit, but still they would be very large. Let me talk a little bit just about the dimension 2 terms. In the Cartan way of looking at things, the dimension 2 terms are either f, the Palatini term, or terms quadratic in torsion or in non-metricity. Now, let us assume that the ground state of the theory is flat space. It's not proven, but maybe in some theory it's reasonable to assume that. So flat space has f equal to t equal to q equal to 0. That's an assumption. Then you can choose a gauge. This is the gauge. I choose theta to be delta mu and GAB to be eta AB. If I make these assumptions, this is just a gauge choice, and it's similar to unitary gauge choice in gauge theories. Then T and Q are just linear combinations of the components of A, and therefore this term here, this part of the action just becomes a mass term for A. So remember that T and Q are just the covariant derivatives of these what I call Goldstone bosons. And so what you see is that the kinetic term of the Goldstone bosons becomes a mass term for the connection. So this is essentially the Higgs mechanism occurring in this theory. And therefore the connection is massive. That's the bottom line. There's another, you can see this also even better in the Cartan, in the Einstein point of view, because when you use this split A is gamma plus phi, then T and Q are linear in phi. They are just linear combinations of those fields. And therefore, in any state and in any gauge, it's going to be true that this SG, this Lagrangian here, were written in the Einstein formalism, is just a mass term for phi. So what does it mean? Well, suppose that the action contains only the dimension 2 terms. Then it means that the only action for phi is a mass term. And therefore, the equation of motion for phi is just phi equal to 0 if the mass matrix is non-degenerate. And phi equal to 0 means that torsion and Q vanish and A equal to gamma. So this is in the case if you assume that the Lagrangian contains only a dimension 2 term. If the Lagrangian contains dimension 4 terms, the equations of motion are going to be much more complicated. They will not imply that phi is equal to 0 as an equation of motion. However, the Higgs mechanism is occurring in this theory. So phi is massive still, and therefore if you look at the theory at low energy, phi is going to be 0. There won't be enough energy to excite that degree of freedom. So independent of the detailed form of the action, it is a prediction of the metric-affine gravity that at low energy, torsion and non-metricity are 0. So you see, in this sense, this metric-affine gravity has higher explanatory power. It gives a dynamical explanation for this fact, namely that the connection is equal to the Levi-Civita connection. This is something that normally we just take as an assumption. It's in page 1 of every book on GR. But here you can explain it dynamically. All right, so what type of states does this theory contain? You have, well, first of all, there's going to be a graviton because there's a dynamical metric. So H is just a symmetric matrix, and so it contains spin 2, spin 1, and spin 0 states. In addition, now we have A or phi, which are 3 index objects. And now the decomposition is more complicated. Suppose you first you pick 2 indices mu nu, let's say. You divide A into a symmetric and antisymmetric part in mu and nu. And then you can take the symmetric part and further split it into the totally symmetric part, I call it TS, and the hook symmetric part, I call it HS. And the antisymmetric part, similarly, you can split into the totally antisymmetric and the hook antisymmetric. So this is one way of separating components, and the other is to look at whether to ask, to distinguish components that are for which the indices are either longitudinal or transverse. So you can have either transverse on all indices or longitudinal on all indices or intermediate things. So you fill up this table and you get here all the states. So you have the totally symmetric part will contain a spin 3 state, and then there will be 3 different spin 2 plus states in addition to the graviton, which is already down here, or maybe some combination of these is going to be the graviton. Then there are some spin 2 states with parity minus, which are weird objects that are not discussed much in the literature. And then there are spin 1 states, either with positive or negative parity, and spin 0, both with positive and negative parity. So lots of states in principle, and whether some of these, which of these states propagates, or whether they are ghosts or not ghosts, that depends on the coefficients in Lagrangian.
What are the meaningful lower stopping?
Oh, because you see, there are two minus states, so I name them the state 2 minus number 1 and 2 minus number 2. I have to give them some name. So the analysis of what propagates. So an interesting question now is which of these theories don't have ghosts, obviously, and this was in the case where Q is 0. This was studied by Sezgin and Van Nieuwenhuizen long ago. Now, if you want to analyze the more general case, it requires knowledge of spin projectors operators for 3 index tensors, and we worked this out a couple of years ago. And then we could study some examples. So some new results, for example, now in the case where t is 0, demanding that the Lagrangian be projectively invariant, and then to simplify things further, demanding that spin 3 does not propagate, and that there's only one spin 2 propagating, only one graviton, then this restricts the Lagrangian to a 6-parameter family. You see, otherwise you would have 40 or 50 parameters, but so by some assumption you reduce the number of parameters. And so in this case, then it can be shown that if these parameters satisfy certain inequalities here, the theory will have no ghosts and tachyons. In particular, this will contain only one mass spin 2, one mass spin 2, and spin 1 plus and spin 1 minus. So, so this is a good theory in a certain sense from the point of view of what it propagates, but it contains, if you now convert this Lagrangian to the Einstein formalism, you will find that it contains R, but no R squared terms. And therefore, it's going to be non-renormalizable. So this is another instance that the old folk theorem holds, namely incompatibility between unitarity and renormalizability is still true. And you see, and further, it's even probably almost certainly true that if you choose the couplings to have this particular form, this form is going to be radiatively unstable. As soon as you compute some loops, you're going to ruin that. So, so we need, in order to make this sure, one needs to do really quantum calculations with these dimension 4 Lagrangians. Some calculations have been done in the past, but they only involve the dimension 2 terms. Okay, so summary is that in general, high derivative gravities are normalizable but contain ghosts. People over time has tried to argue that the ghosts perhaps are not there or are not important, and this line of thought has been pursued and expanded also recently quite a bit. If it was asymptotically free, then it would be UV complete. But asymptotically free also means that when you go to from the ultraviolet fixed point to lower energy, you're going to hit, there's going to be a regime of strong coupling. So that maybe is a way of generating the Planck scale. There's speculations in this direction. For me, high derivative gravity is a stepping stone towards metric-affine gravity. It's easier to understand high derivative gravity. And metric-affine gravity, as I said already, it makes gravity similar to other gauge theories. And the question then, you see, I told you that there's a Higgs phenomenon occurring, and so there are some similarities to electroweak theory. So just like in electroweak, the central question is what is the origin of electroweak symmetry breaking? I think that the central question for a theory of spacetime ought to be what is the origin of the breaking in this case, which means, and since the order parameter is the metric, what is the origin of the vacuum expectation value of the metric? So given that this is a question I think is very central, I find that there is very little work going on this. Well then, as I said, quantum properties of metric-affine gravity need to be explored. Thank you.
We have time perhaps for a question. Yeah, please, Josh.
One question is, could you clarify a little bit more, because I came a little bit later. Eventually, do you have a Higgs mechanism or not? And what breaks to what?
Yeah, there's a Higgs mechanism of the type that in particle physics one would call a Higgs-less Higgs mechanism. That is when you have some gauge theory that is coupled to Goldstone bosons. So you have the Goldstone bosons, but you don't have the radial mode. So when you go to unitary gauge, the gauge field becomes massive, but there is no massive Higgs field in this case.
I see. Then you mentioned the tachyonless and ghostless conditions. They can be destabilized in.
Well, that I don't know, but for sure. But I think probably yes. Yes.
And then at the end, you mentioned that if you have asymptotic freedom, you might have a strong coupling theory. And is there where you start to meet? I noticed in some of your papers you have this safe gravity.
Well, in asymptotically safe gravity, can I draw something?
Yes, sure.
Maybe okay. So this I don't need actually. Usually we think of this, there's some, well, this is energy here, momentum. And actually, let me tell you first what some people speculate. If you have if this theory is asymptotically free, there's this coupling lambda that will goes to zero, but will become strong here at some point. On the other hand, we know that gravity, so let's assume that this scale here is the Planck scale. On the other hand, we know that there's a description of gravity at low energy in terms of the metric and the Newton coupling. So Newton coupling times momentum grows like this. So this is GP squared. No? So you have you would have a weakly coupled regime at high energy, weakly coupled regime at low energy. This is like QCD, where you have quarks and gluons here, and you have pions there. And so and here there's something questionable. In asymptotic safety, it looks a little bit different because this coupling here then reaches a fixed point. Yeah. But I think there may be some relation between these two pictures, actually. It's quite possible that the two can be, that even, yeah. There's more similarity than.
Thank you.
I believe there was another question back there.
Yeah, thank you very much. My question was in the same direction as George's, I think. I mean, I didn't quite see what is broken by the Higgs mechanism. And if so, are there some parameter choices maybe where you have different stages of breaking? Or
yeah, sorry. So
reduce number of parameters maybe.
So what is broken? I didn't say it. I apologize. It's local. The freedom of choosing frames locally. It's a local GL4 gauge. Local GL4 gauge transformations is present if you are in the formalism that I described, where you have both theta and g, and that is completely broken. So yeah, GL4 is completely broken. What remains is just diffeomorphisms.
So there's no points where you have maybe a partial breaking and some enhanced symmetry, maybe for particular value of parameters.
In principle, there's nothing. It may be, but I don't have any examples in mind.
Thank you.
I just wanted to ask, can you please show where does A first appear?
A?
Yes. Go to the slide.
Sorry?
Can you please go to the slide?
Yes. Yeah.
You define it as an independent connection. You just define it like that. Okay.
Yeah.
It's not.
You have the tangent bundle, connection on the tangent bundle, independent of the metric and everything else.
And the gauge group is.
Well, the gauge group, as I said, if you're a mathematician, the gauge group is the automorphisms of the tangent bundle. Yeah.
Okay, thanks.
Padilla, did you have a question?
About your the connection with the spectral action, which of course I find very suggestive. I think it's clearly there is something, although the two are somehow dual, because for the cone standard model there is a cutoff, which is very important. So you do the trace, but whatever is below a certain cutoff, and then you expand in the cutoff. Here instead, it is somehow taking care of the ultraviolet. If I understand, you sort of saying that in the ultraviolet, the R term doesn't count and only the R squared. So there are connections, but they seem to be dual to each other. If we had still Lacoste, I would have organized a meeting between the two communities in which we could really sitting down for a couple of days and really we can try to discuss it.
Yeah, maybe a meeting of communities is not necessary, but the way
we are not that big.
Yeah, but the way I see it is that essentially in non-commutative geometry a la Con, you assume that basically in the ultraviolet there exists only the fermions. And therefore you compute an effective action that comes from the fermions. And that is some trace of a function of the Dirac operator.
With a cutoff.
With a cutoff, but the cutoff is some lambda. And you morally you would identify that lambda with a Planck mass, let's say.
Yes.
Yeah. And then at that point, all the bosons begin to propagate. And then you can do the aromatization group down from the Planck mass. And then you have a trace that contains not only the Dirac operator, but it contains the propagators of all the other fields, including the bosons. So when I do my RG, I always assume that all the fields are there. I never rule out any field. Whereas for some reason you rule out all the fields except the fermions above the Planck scale.
Yeah, but
that is
you don't have the Higgs. You have a Higgs Higgs, while in the other one. Okay, well, the meeting of community is probably useless, but probably you and I.
Yes, yes.
Yeah. So we have one more last question here.
Yes, I was wondering what happens if you study the same type of gravitational Higgs mechanism, but under the assumption that the ground state is a fully degenerate geometry rather than a flat Minkowski space.
Fully degenerate means G equal to 0. That would be the unbroken state.
Yes.
I don't know, you see, I don't know how to write the action in that case. That is where the show stops. For the time being, at least.
Okay, so let's thank the speaker again. We are running a bit late. Oh, there was a question on the. No, we checked that. We checked that actually. So the next speaker is Evgeny Skvortsov. It's a remote talk. Is he online?
Hello, can you hear me?
Yes. Okay, very good. Okay. So could you
just
bring up your slides, please?
Yeah, yes. By the way, could you please make the second copy of me also panelist, because I'm connecting from tablet. So if you want to see me, I can also connect from laptop.
Is that something you can read?
Right, and where it is? It's here.
So while you bring it up, let me just say the format is 25 minutes talk. 5 minutes for questions. And I'll give you a warning around, I don't know, 6 or 7 minutes before. Okay?
Yes, okay, just let me check the equipment. Hello, can you hear me?
Yes, we can.
Okay, should work. You hear me, you see me, and you see the slides, right? Could you please confirm?
Yes, this is good. Yeah.
Okay, good. So then I can probably draw. So can I start?
Speaker is Evgeny Skvortsov, Integrable Models from Non-Commutative Geometry. Please go ahead.
So thank you very much for invitation, for giving this opportunity. I'm really sorry for giving talk online. I was supposed to be there, but then some personal commitments didn't allow me to do that. But next time for sure. This is a great series of conference. So as in any online talk, let me start maybe with the main messages because, well, in case connection disappears. So I have a couple of main messages and just one suggestion. So one of the results I would like to present is the construction of new class of integrable models that are based on associative algebras. So given any soft associative algebra, soft means that you can deform it into one parameter family of algebras. That's the usual thing for, say, deformation quantization. So given such an algebra, we can construct highly nonlinear partial differential equations that nevertheless have solution with the help of Lax pair that we provide. But in fact, what we actually did was to construct a new class of strong homotopy algebras, A-infinity algebras that are based on associative algebras and can be thought of as a kind of non-commutative deformation quantization of those algebras. And given any A-infinity, you can easily construct L-infinity, which in practice means that you have some odd nilpotent vector field on some space that you can call target space, so that you can write sigma model type of equations like this. And then our result is that for the class of algebras that we constructed, these equations turned out to be integrable. So, but where to get such soft algebras from? Of course, one source I already mentioned is deformation quantization, but there is an interesting and little explored extension of deformation quantization to Poisson orbifolds, to Poisson manifolds that have symmetry, which is usually the case. And well, it doesn't yet have its Kontsevich-like theorem, but in fact, it is this case that has some relevance for applications. So now to applications. Why are we interested in such esoteric structures like strong homotopy algebras at all? It's because we believe that they are actually realized in some models of physics, which are represented by three-dimensional conformal field theories known as vector models or Chern-Simons meta theories. And in fact, with the help of these structures, we can explain certain remarkable dualities in these models that were conjectured recently. Last but not the least, the results are based mostly on papers with Alexei Sharapov and the spin-offs of our research on higher spin gravity, which I have nothing to say today. Good. So coming to the first part, integrable models. Of course, a hallmark of an integrability is Lax pair, which is a pair of two matrices or operators, where one of them, called A here, plays the role of connection, but say in one dimension, and there is another matrix L that satisfies covariant constancy condition, which immediately tells you that you have infinitely many, maybe not independent integrals of motion that can be constructed as traces of powers of this matrix. So what I suggest here is a natural generalization of Lax pair to any dimension that I will need later. And natural extension is as follows. Let us take some manifold M, can be d-dimensional. It is equipped canonically with a Deram or exterior differential. And let me take a connection of some algebra. Well, it has to be Lie algebra, but in my case, it will be obtained from an associative one. So let me take some connection A
of a Lie algebra, and also a zero form on the same manifold that takes values in some representation of this Lie algebra, which for simplicity I take to be the adjoint one. And then what I suggest to be a generalization of Lax pair to D dimension is to write the following equation. So we require connection to be flat, and this matter like a zero form to orbit covariant constancy relation. Then, of course, our job is essentially done here because locally we can easily solve this pair of equations in a pure gauge form like these. And if algebra admits some kind of trace operation, you can also construct infinitely many of integrals of motion that are D-closed. So, but okay, so this system is trivial in a sense because we can easily solve it. So now let me try to construct something very similar, but where no obvious solution can be found. So I take exactly the same field content like on previous slide. So connection of some algebra and a zero form. And I write the same system to begin with, covariant constancy and flat connection. And now what I would like to do is to add interesting nonlinearities. Because form degree is fixed here, what stays on the right-hand side has to be 2 form. So the number of a's is fixed to be 2 in first equation, it fixed to be 1 in the second equation. But you can have plenty of nonlinearity thanks to zero form C. So in principle, you can have infinite series in these maps that we can call vertices. And I also would like to require these equations to be formally consistent in the sense that they don't have any hidden algebraic constraints on the fields, which means that, well, in practice, you just apply D to both equations, substitute equations into equations. On the right-hand side, you have 0, of course, because D is nilpotent. Sorry, on the left-hand side. On the right-hand side, you might find some algebraic constraints on your fields, and I don't want that. So this is known, of course, as Frobenius integrability, and unfortunately, it doesn't have anything to do with being integrable in the way I want, but it just tells you that equations are formally consistent. But nonlinearity makes the system hard to solve, and this is what we want. And in principle, just maybe side remark is that any gauge theory you can think of, Young-Mills, gravity, supergravity, can be written in such a way, if you can. But as a matter of principle, it can. So, but let us maybe zoom out a little bit on the system to see what is the actual problem we're trying to solve. To do that, I just pack my fields into sort of string field phi, and then the equations I'm looking for have sigma model type. So I have d phi that equals, well, some nonlinear function of phi. And form degree tells me that Q has to be, has to be an odd vector field. It has to have degree 1, while formal consistency, Frobenius integrability, implies that this field has to be nilpotent. So in fact, we just have one of the possible definitions of L-infinity algebra in some space, which we can call target space. This is the space where these fields take values. So in fact, we're looking for some L-infinity algebra. If we have one, we can write down this system of equations, which of course doesn't imply it's integrable. Or other way around, if somebody gives you such a system of equation, there is a L-infinity algebra behind it. And now our problem is, of course, how to find the vertices and relate them to the algebra I started with, to the algebra that defines what I denote by star here, the product, well, which a bit formally means how to find an L-infinity algebra that extends in some way a given algebra and its module, because this initial system I started with just tells me it's another way to tell us that we have some algebra and some module of it. In this case, it's an adjoint module. So then L-infinity deforms this structure in some way. Well, in fact, our L-infinity will come from A-infinity. Well, if L is a generalization of Lie algebra to strong homotopy algebras, then A is a generalization of associative algebras to strong homotopy algebras. You don't have to know what the actual definition means. I will never need it. But if you know, that's good, of course. And our L infinity will result via the usual anti-symmetrization map. So this is again extension to strong homotopy case of the usual way to construct Lie algebra by defining your Lie bracket to be just commutator. If you have some associative algebra, you can always construct a Lie algebra. And there is a strong homotopy algebra extension of that statement. And this is what we'll see realized in practice. Okay, so the problem is to construct these vertices and relate them to the initial algebra. And now I really need this initial algebra, whose product is star here, to be associative. And then our result is the following. So under certain technical assumptions that I have no time to tell you, you can prove that this system of equations admit non-trivial deformation if, and in fact only if, the underlying algebra admits one parameter family of deformation. So it's a soft algebra. So let us just assume this is true so that our initial star product here can be deformed with the help of some maps called phi k here, and h is a formal deformation parameter, which of course has nothing to do with actual Planck constant. So we can deform the star product into some product denoted by circle here in such a way that the circle product is still associative, which of course imposes infinitely many constraints on these bilinear maps phi k. And well, specialists can immediately tell us that the very first map phi 1 has to be in fact Hochschild cocycle, non-trivial one. Okay, in principle, we have several ways to construct all the structure maps so that they form A and hence L infinity algebra, but this requires a lot of definition from non-commutative geometry, which again, I have no time for. So let me just give you a couple of examples how you can construct such maps. For example, the cubic vertex in this equation originates from a obviously trilinear map that looks like this. It looks like a little bit if you replace H bar with an element of an algebra, which of course doesn't make any sense because H bar is a formal deformation parameter that commutes with everything, while well, U here is an element of an algebra. So you can't just do this within, say, the category of associative algebras, but if you extend everything to strong homotopy algebras, you can. But it's not that easy. For example, if you look at the quartic vertices that originate from map called M4 here, then yes, the first term looks like you replace H square with two elements of an algebra, but there is a second term. And in general, if you want to write order n vertex, there will be many terms with phi, with these bilinear maps phi nested into each other in different ways. And but one can check that altogether, these structure maps Obi Stashev relations, where this double bracket is Gersten-Haber bracket. So we have A infinity algebra. And as a result, we have L infinity. And as a result, we can at least write this system of equations. And we can show, of course, that all these vertices are non-trivial. So there is no redefinition that would take us back to the system we started with, which is just covariant constancy and flat connection. So this system is non-trivial, and we can go back once we add at least one such vertex. And now what I would like to show is that this system is integrable in some sense. So it's integrable in at least two ways. First of all, we can easily construct all solutions to this system of equations, and secondly, there is a way to write many interesting integrals of motion. Let me take an advantage of using different colors here, so that my nonlinear system that I want to solve has this red fields in it. While the way I solve it is with the help of auxiliary Lux pair. And the fields in this Lux pair are blue fields. They are different from red ones. And since I told you that all these vertices are somehow constructed from these maps phi that deform a star product, well, it's not actually a star product. It doesn't have to be star product. It's just denoted by star. So these maps phi deform the star product to some circle product. So you should not be surprised that the Lax pair is a trivial system of equations. Trivial in the sense that I already showed you that we can solve it in a pure gauge form. So it's a trivial system of equation where fields take values in this fully deformed algebra, so that everything depends on this formal Planck constant. And now the statement is that you can construct exact solution of this red nonlinear equations by taking any solution of this blue system, which is easy to solve. And the map looks like this. Again, there is a very simple way to write it, which requires, say, 30 minutes of definitions. So it's better just to illustrate how it works in general. So you take some of these blue fields, differentiate them with respect to this formal deformation parameter, and also form some nonlinear combination like here. And then you can check that order by order, this gives you a solution of the red nonlinear system. And there are similar maps in the literature, for example, Nicolai map, and I think there is at least one talk about that at the conference. And maybe many people are familiar with Seiberg-Witten map, which is a way to map commutative, usual commutative Young-Mills theory to a non-commutative one. And this map is similar in the sense that we have a map from already non-commutative, but very simple system of equations to another system, which is even more non-commutative and more non-linear. So it's kind of a Seiberg-Witten squared, because the starting system is also, in a sense, non-commutative. Okay, so this is the end of the first part. Given any one parameter family of associative algebras, we can construct some nonlinear system of partial differential equations, and we can also solve them. Of course, it needs to be checked that, well, system is nice, makes sense, and so on. And this a lot depends on the concrete algebra that you plug into this construction. And in principle, there are two large stocks of soft algebras. One of them is to take any finite dimensional associative algebra that depends on parameters. Of course, it cannot be semi-simple. It cannot be just matrix algebra. That's forbidden. Moreover, the problem of classifying of non-semi-simple associative algebras is wild. Well, which probably means that we will never see this classification completed. But on the other hand, it gives you a lot of infinitely many of systems of this type that you can construct by taking any of infinitely many soft associative algebras that are finite dimensional. Another natural source of soft algebras is deformation quantization, because this is what we do there all the time. We take some, in fact, commutative algebra of functions on phase space. We deform it by Poisson bracket and look for other terms. And here the solution, of course, is essentially known. But what shows up in practice, well, in some applications that I'm going to talk in the last part, is an extension of this construction to Poisson orbifolds. We also know some of these examples, for example, as fuzzy spheres. So let me say a few words about that, because some of these examples have been known for 80 years or so in the context of quantum mechanics. So first of all, just a brief reminder on usual deformation quantization. So the problem is to deform the pointwise product of functions on phase space with the help of any Poisson bracket into something that is called star product, so that star product is associative. And then higher order terms can be extracted from Kontsevich formality theorem. And of course, if your phase space is flat, boring R to N, then the solution is given by Moyle-Weil star product. And all these terms can be also interpreted, as was shown by Cataneo and Felder, as Feynman graphs resulting from quantization of sigma model on the disk. But usually all manifolds have some symmetries. It's even hard to imagine some manifold that doesn't have any symmetries at all. So suppose we have a Poisson manifold with some symmetries, and we picked some discrete group of symmetries to play with. Then one can think about two algebras of functions associated with such a manifold. The first one is just to take the algebra of functions invariant under all these symmetries, and the complementary algebra is to take what's called cross product. It's kind of semi-direct product of these functions with a discrete group of symmetries you have. Okay, so then any of these algebras, of course, has the usual Kontsevich-like deformation. That is, well, that can be extracted from his formality theorem, but you can ask if there is anything else. And in fact, it turns out that in many cases, there are new directions of deformation quantization. So there are new independent deformations, independent from the usual Poisson bracket, that these algebras can have. And finding some analog of formality theorem for these algebras is still an open problem, of course, but as a good approximation, perhaps one just should have a look at the quantization of Poisson sigma model on orbifolds. But in any case, if you have Poisson manifold with symmetries, and say the simplest symmetry is some reflection that forms Z2, then your algebra can have two deformations. One of them comes with the usual Poisson bracket, and Planck constant is HK, like Kontsevich. But there can be another deformation that is usually called in the literature non-commutative Poisson structure. So you can have two parameter family of algebras. And in fact, okay, what just happened? No, fine. Okay, and in fact, one such algebra has been known since 50s in the context of quantum mechanics, and it's closely related to just canonical commutation relations. So let us take the algebra of Q and P's that will be canonical commutation relations. Of course, this algebra can be understood as a deformation quantization, star product being just Moyle while, and we know that this algebra is rigid. It cannot be deformed once again. It has been already obtained as a deformation of classical phase space, but now not anymore. So you can deform it once again. However, let us add an obvious symmetry denoted by R here, which is reflection symmetry that flips sign of Q and P. And we can consider the algebra of functions of Q, P, and this operator R that realizes this symmetry. Then this algebra is known to be soft, so it can be deformed. And in fact, at least in this case, the entire deformation can be described by these deformed canonical commutation relations, where you see one more parameter denoted by nu here that enters, of course, with this R with a symmetry operator. And well, this was first obtained by Wigner and then studied by many people. And this algebra is known under many different names, for example, Parabolic Oscillators. So if we restrict ourselves to the even subalgebra of this algebra, then again, it's well known that this algebra admits a deformation, which, for example, can be described as quotient of universal enveloping algebra of SP2. And it's also known as fuzzy sphere or non-commutative hyperboloid, depending on the signature you consider. And of course, there's a famous paper by John Mador on fuzzy sphere that discusses exactly this case at some point. Well, in some physics context, this algebra is also closely related to anyons. Okay, so the conclusion here is that at least orbifold R2Z2 admits a second quantization on top of the usual Moyle-Weil product, and we will need it in applications. Good. Which applications? Because there are very few applications of strong homotopy algebras to actual physics. I mean, they are useful for many other reasons, but talking about actual physics, there are not so many. And I hope we found one. And this is application to a second order phase transitions, which are understood as conformal field theories in 3 and maybe higher dimensions. So what are these theories I'm talking about? These are known as vector models, or more generally Chern-Simons meta theories, and they extend all the way from Ising model to ABGM type theories. And to describe the simplest instance of dualities and in applications here, I need 4 basic models of this type that you can construct as follows. We are in 3 dimensions, and we can take a free scalar field, number of them, or interacting phi to the 4th theory, which at the fixed point is exactly the Ising model or Wilson-Fisher. We can also take number of free fermions or interacting fermions, so this model is known as gross niveau. Also in 3 dimensions, we have an additional luxury of being able to add Chern-Simons interaction. So we gauge some global symmetries here, hence covariant derivative on the slide. And we add Chern-Simons action to all of these. And these are called Chern-Simons meta theories, simplest of those. You can add supersymmetries, you can play with different matter contents and so on. So these are the simplest models of this type. Of course, they describe some physics because—
You have 5 minutes?
5 minutes, very good. So I'm almost done. So of course, these models describe some physics. Well, they break parity in general, and they depend, which is important, on 2 parameters: the number of fields n and Chern-Simons level. So in the large n limit, which I will consider, you can form 't-Hooft effective coupling lambda n over k, and in principle n and k are discrete. But in the large n limit, lambda becomes almost continuous. And what these models are also interesting for is that they were conjectured recently to be related by a number of dualities, in particular by 3-dimensional Bosonization duality. What's that? Well, let me place at the corners of this diagram these 4 basic models with Chern-Simons coupling basically turned off. So you have free boson, free fermion, gross niveau, Wilson-Fisher. Now I turn on Chern-Simons coupling, and as a result, I have 4 1-parameter families of conformal field theories. Now the conjecture is that they coincide pairwise. So you can take Wilson-Fisher, which is a phi to the 4th theory coupled to Chern-Simons. You get a 1-parameter family of conformal field theories that in fact end up in free fermion. Or I can take fermion, couple it to Chern-Simons, and end up in, well, an Ising model. And all the way from here to here, these theories should describe exactly the same physics. That's a conjecture. And there are many tests of this conjecture. And for what I'm going to tell you, I'll need just one fact, that the simplest gauge invariant operators in these models are so-called higher spin currents, which are some bilinears sandwiched with derivatives. Since these are called higher spin currents, as names suggest, they should be responsible for some higher symmetries, and indeed they do. If you take a very large n limit, or just take some of these free theories that we had on the previous slide, then you can construct these operators. They are exactly conserved. So on top of stress tensor, we have infinitely many of these higher spin currents, and they form some infinite dimensional algebra of symmetries, which can easily be understood as Weil algebra again. So you have an algebra of functions of Q and P on some space, and this algebra is isomorphic to the algebra these higher spin currents form. So in some sense, one can say that free or quasi-free conformal field theories, they give rise to associative algebra. Well, usually symmetry is realized by Lie algebras, but in this case, the Lie algebras we have, they originate from associative ones. And again, not surprisingly, you can easily construct invariants of these algebras, and these invariants compute exactly the correlation functions of these higher spin currents. So, but this was about free or quasi-free theories. So in these theories, we have currents that are exactly conserved. They form charges, charges form algebra, and charges act on higher spin currents. Very nice. But in actual Chern-Simons meta theories, Ising model, and so on, these currents are not conserved. In the large n limit, this non-conservation is a small effect, but it's non-conservation. And what's remarkable and special about vector models are this non-conservation operator is not just some random operator, otherwise the symmetry is just broken and you can no longer use it. It's built out of the currents themselves. So in a sense, currents are responsible for their own non-conservation. And then you can ask, okay, what's the right math to describe that? Because certainly it's not a Lie algebra, you lost your symmetry, but in fact, you have not lost it completely, it gets deformed. And it gets deformed in exactly the way that we already know. So you have a Lie algebra that originates from associative. You have some module of it, which are higher spin currents themselves, and you try to deform the entire thing together. And this is described by the L infinity that I played with in the context of this integrable theories, the same type of L infinity algebra. Therefore, and this is the last slide, therefore, if we just study this L infinity algebra and invariance that we can have, we can learn many interesting things. And what we learned is that L infinity that is relevant for Chern-Simons meta theories depends on two parameters, which are for us phenomenological, but in practice they can be related to K and N. Also, there is exactly one invariant that can play the role of endpoint correlation functions, and we've checked at the zeroth order that they indeed reproduce correlation functions, and but they can be deformed to full-fledged invariants of this L infinity algebra. And in fact, there is even simple generating function for these guys. So as a result, so these results explain the three-dimensional bosonization duality, since we could fix the form of endpoint functions of higher spin currents just from the symmetry. So it doesn't matter if they're made out of fermions or bosons or in some other way, it doesn't matter. Symmetry fixes the form of all endpoint functions. And in fact, there is a simple consequence of that endpoint functions have to have very special form. It has to be finite sum of fixed structures times parameters. So you can't have sort of non-trivial dependence on coupling constant. And that's not important. Let me come to my summary. So any soft associative algebra leads to a formally integrable system of classical equations, or this can also be understood as constructing L infinity algebra that in fact follows from A infinity. And it would be interesting to study new source of these soft algebras, which results from deformation quantization of Poisson orbifolds, because this extension of deformation quantization doesn't yet have its formality theorem. But in practice, we need this type of algebras. And maybe the main message of the last part is that higher spin symmetry can be kind of new Virasoro symmetry that works in dimension higher than 2. Of course, it works in a completely different way. So the only property shared by the two symmetries is that they're both infinite dimensional. But otherwise, the way they work is completely different. Higher spin symmetry gets deformed to some L infinity, while for simplest application of Virasoro algebra, you don't need more than just basic representation theory of this algebra. And then classification of L infinity invariants in specific case relevant for three-dimensional models implies three-dimensional bosonization duality. So let me stop here. Thank you very much. And well, here are some papers just for reference on which this talk is based on. Thank you.
Thank you. We are running way over time, but perhaps we can have one or two short questions, if there are.
Hi, Zhena. Thank you for a very nice talk. My question is, when you said that you get three-dimensional bonization duality from L infinity, you mean you get it in a way as L infinity quasi-isomorphism? That's the statement?
Well, no, it's even simpler. Just so you have actual models, these Chern-Simons meta theories, where there is sort of closed subsector of higher spin currents. These higher spin currents in principle form charges, but charges are no longer conserved. So if you want to describe mathematical structure where algebra and its module higher spin currents gets deformed together, the right mathematical structure is L infinity. And then, of course, you can ask about invariance of this L infinity algebra, and there could be none other else than correlation functions. So in a sense, it's quite mundane application of L infinity. So we don't need any quasi-isomorphisms or more advanced notions. So this L infinity is exactly the one realized by higher spin currents together with the charges they form in vector models.
Thank you.
One more question.
Hello. You know, there is this highest spin free Lagrangian, which was written by Sink and Hagen and also Fronsdal.
Yes.
So, and then you try to deform it, which means introduce the interaction. And that's really failed. So
Yes.
my question is that when you want to deform your algebra, as you say, and I mean, finally, can you really state that you find the Lagrangian and the symmetry of that Lagrangian?
Well, thank you very much for this question. Excellent question, because so I think one of the hidden messages here is that, well, first of all, you're absolutely right. If you just try to construct, I mean, higher spin theories, you face enormous amount of troubles because somehow higher spin symmetry doesn't want to live in local field theories. But my message is that you can forget all of that, even though there are some consistent models of higher spin gravity, but they are either non-unitary or, I mean, something else goes wrong from fundamental point of view. But my message is that you can forget all of that. You can just go to conformal field theory. And in conformal field theory, first of all, in free models or quasi-free, you find higher spin symmetry just as it is, realized by higher spin currents. It's well-defined. I mean, obvious all the axioms of quantum field theory, and then you can look for what happens in these vector models when you turn on interactions, and then higher spin symmetry gets deformed, but again, nothing goes wrong. So, in a sense, if you're not interested in the in the struggle of some people, including myself, to construct higher spin gravity, you forget all of that. You just take a higher spin symmetry, and it's realized in certain conformal field theories that are closely related to some physical models. So in a sense, I don't have any actions. I don't have anything useful to say about that. Well, except that maybe if you try to play exactly the same game for higher spin theories, you run into the usual troubles. I can't solve them at the moment with all the technology that I explained. But on the conformal field theory side, higher spin symmetry is well defined. That's maybe the main message.
My name is George Savidi, and I want to say that I was working on Young-Mills deformation, and some publications are available. So if you're interested.
Yes, okay, yes, thank you.
It can be done as a more private discussion. So let's thank the speaker again.
Thank you.
As you noticed, we have many social events every day. Something. Today is the Greek night in Tripas, and all you have to do is to sign that you are interested, because we have to fix buses and things like that. So just please sign. Any accompanying person is welcome, so no problem in the number. Just we want to know numbers. This holds also in particular for the boat trip, because the boat trip, there is a restriction on there is a lower bound in the number of participants that they don't take us. It's not profitable for them if we are not enough. We have to pay more or something. So just keep signing, and